The topic here is solubility equilibria, and we're going to learn a little bit of review of how equilibrium equations work and a little bit of review about what solubility is. Hopefully we can put this together and link into some previous learning. So let's start with that word solubility. So when we learned about solutions, we learned that solubility, maybe we learned solubility means the ability to dissolve, but that's not entirely correct. I like to say solubility is really the amount that dissolves. The amount that dissolves. So it's a numerical measurement. But let's start with that idea of soluble. You might recall that a good periodic table may have on it some solubility rules that help you predict which things dissolve and which things don't. And when we studied this before, it was an either or, either it dissolves or it doesn't dissolve. And in reality, there's actually a degree of dissolution that takes place. So now we're going to start quantifying how much of it actually dissolves. When something on here says insoluble, such as most hydroxide salts are slightly soluble, or let's try a different pen there, slightly soluble, or maybe it's described as insoluble. Insoluble doesn't mean none of it dissolves, but a small, sometimes tiny amount does dissolve. So we're going to look at how we can predict how much of that dissolves. We do that using the concept of equilibria. Recall that we studied equilibrium equations and learned that reactions that we've been kind of assuming all this time are just going in one direction actually are happening in two directions at the same time. So as the reactants are becoming products, the products go back and form reactants, something that looks like this. And then the way we notate that both reactions are going on at the same time, rather than just writing an arrow that shows a one-way reaction, we've started to include two arrows for those equations we want to show are in equilibrium, forward and reverse reaction going on simultaneously at the same rate. All right, let's take an example of mercury bromide. So there's a little diagram over on the right side that shows what mercury bromide might look like. In this diagram, looks like they've modeled some mercury atoms as these purple spheres and some bromide atoms as these brown spheres. And if I could just zoom in on this, let's try to identify a couple things in this diagram. So first of all, this crystalline arrangement of brown and purple spheres represents the solid. The blue, of course, would be all of the water. And then in the water, we see these kind of solo brown spheres and purple spheres. And just based on the amount of these, I can tell the brown ones must be the bromide ions. Looks like there's more of those. And the purple ones then would be the mercury 2 ions. Mercury 2 is a 2+. And so we can kind of visualize that some of these floating ions may come together in just the right way that they will stick onto this crystal and kind of grow the crystal a little bit in a process that we call precipitation. But at the same time that's going on, maybe in another place, some of these ions may kind of come apart here and get back into the water and become aqueous ions. So while we have precipitation going on in one place, we may simultaneously have dissolving, what we call dissolution, going on in another place. And that's going on all the time. This reaction never really stops, but we just get to a point where they happen at the same rate. Every time a precipitation occurs, a dissolution occurs. So dissolution, again, for the sake of kind of a reminder of our definitions, dissolution is just a fancy word for dissolving. Solid becomes aqueous. And then crystallization or precipitation, that's when the aqueous ions solidify. They turn back into a crystal, crystallization. So aqueous ions turn into solid. And these ionic solids are kind of crystalline, these repeating organized structures. All right, we can show both of these in a really convenient way when we write out an equilibrium equation. So this is the solubility equilibrium I was just describing with mercury bromide, solid on the left, mercury bromide. And then as we move from left to right, we're dissolving it. So that top arrow represents dissolution, forming the ions out of the solid. The ions, note, are aqueous. So these are dissolved. The right side represents a solution. But then at the same time as dissolution occurs, we also have precipitation going on as you take those ions and turn them back into a solid. And those go on in equilibrium. So the question really isn't like, which way is this reaction going? It's going both directions. But we want to know, where does equilibrium lie? Does it reach this point when they're going on in both directions at the same rate, when there's lots of ions dissolved, in which case we might say it's more soluble? Or does it reach that equilibrium when there's only a tiny bit of ions that have dissolved? Does it favor the left side? Is it less likely to dissolve? Right. In order to describe this, we're going to need some numbers, but let's start with writing out these equations. I want to review with you how to write a solubility equilibrium equation, and then we'll look at an expression that we can plug numbers into for the next part. So how do we write a solubility equilibrium equation? This is going to tap into some other prior knowledge you have. I'm going to write this for calcium hydroxide with you, but in order to write this out, I need to know, what is calcium hydroxide? I need to break this into its parts. Grab a periodic table. If you don't remember this stuff, we can find a lot of good information on our periodic table. We're talking about calcium hydroxide, so I can find calcium on my periodic table right here. And on your table, I bet you wrote those are 2+ ions. The entire column is 2+ ions. The column next to it has all of our 1+ ions, and over here, these are the 3+ ions. Some of these things we can predict the charge for. So calcium I would predict is a 2+ ion. The other half of this hydroxide, I can find information about that on the back of my periodic table. Maybe I've even memorized this. OH with the charge of 1-. So calcium hydroxide is made of those two things, calcium being the 2+, hydroxide being the 1-. And we learned how to write that together so that it's neutral by crisscrossing charges. So if I had a 1-, I could crisscross the 1, write it next to the calcium, crisscross the 2, put it on the outside of some parentheses next to the hydroxide. Okay, calcium hydroxide will look like this then. Let's write it here, CaOH2. When you write a solubility equilibrium, you always start with the solid on the left. So we're going to assume that the calcium hydroxide is in the solid form, and then we add it to some water. And what happens when it hits water? Well, it may or may not dissolve. Some of these things dissolve completely, like salt, sodium chloride. We would probably just draw one arrow and say it all dissolves. For this substance, we'll write an arrow to the right to show that some of it dissolves, but then we'll include another arrow to the left to show those dissolved things can go back and turn into solid calcium hydroxide. What does it look like when it dissolves? This is the tricky part when you're learning how to do these. How do I break apart calcium hydroxide? Well, if you know how to put calcium hydroxide together from the ions, to show it dissolving, you basically just separate those ions. Separate the compound back into calcium, that was 2+ charge, and hydroxide, which is OH, 1-, or we can just write a minus. And note that the ions are what dissolve. Those are aqueous. The combination of the two, we write that as a solid. There's one final step in doing this. We've got to remember to balance our equations. So rather than putting this in parentheses with the 2 out here, that's not the way we balance equations. We're going to balance the equation instead by using coefficients. Put a 2 in front of that. So this particular dissolution process creates 3 ions, 1 calcium and 2 hydroxides. Let's look at the next example, which is for barium sulfate. In the barium sulfate example, I need to look up barium and sulfate unless I've memorized those. I see barium is a couple lines below the calcium, so right there. and that means it's also a 2+ ion. And then if I look over on this chart, I see sulfate right here. It's a lot quicker when you start to memorize your ions. So barium in the same family as calcium must have the same charge, 2+, and sulfate you might just memorize is SO4 2-. Put those together in this combination. That's how the solid exists, BaSO4. No need for parentheses. That's the solid. Show it dissolving by breaking it into a barium ion that's aqueous and a sulfate ion. Note that the polyatomic ions do not break apart. They stay together. OH stayed together. SO4 with the 2- charge, that stays together. There we go. This one, we don't really need coefficients, but if you want coefficients, you'll note that there's one of each of those. This one doesn't make as many ions. All right, let's try one more. Lead 2 phosphate. This one's a little more complicated. Let's see if we can write the formula for lead 2 phosphate, knowing that lead, the name of it tells me, is a 2+ ion. And without running over to the back of my periodic table, I'm just going to write out PO4 3- from memory. All right, we're going to try to put those two ions together to make lead phosphate, the solid. That should look like this, PB 3SO4 in parentheses 2, the solid, will dissolve. That solid will dissolve into lead ions. You may be tempted to keep the 3 right where it is. Don't do that. This is not a triatomic ion. Most ions break into individual single ions, lead, the charge being 2+. And then we can keep that polyatomic ion together. We'll include the 4. That's part of the polyatomic ion. That is a 3- ion. So how do we take care of those numbers down there? We balance the equation with coefficients. Looks like there will be 3 of those lead ions and 2 phosphate ions. I forgot to do this in the last equation. Let me make sure I don't forget again. This equilibrium equation should have equilibrium arrows. One showing it dissolving and one showing the dissolved ions going back to form the solid. So don't neglect the double arrows in your solubility equilibrium equations. Last step I'd like to show you is called writing the equilibrium expression. So equilibrium expressions we've written before, they have a K value equal to, and then in a general sense, it's always the products on the top and the reactants on the bottom. And if there are coefficients in the equation, remember those become exponents, so don't forget to raise those to the appropriate power. Also, remember we learned when writing equilibrium expressions that we do not include anything that is a solid or a liquid. So only the things that are aqueous or gases. Let's try this for our equations. I'm going to write an equilibrium expression for part A right over here next to it. So this is my equilibrium expression. K equals products, each one written separately. Now these products have a little bit of extra notation in them. I don't want to forget to write the charge. It's got a charge with it, 2+. I don't need to include the AQ in my equilibrium expression. That does tell me to include this ion though, because aqueous substances do get included. Also notice I'm not writing in the coefficient, the 2, in front of or with the OH ion. Instead, I'm writing the 2 as the exponent on that ion. Okay, normally we would then take the products on the top, the reactants go on the bottom. But note in this example, in each of these examples, that we've got solid substances written as our reactants. which means we don't need to put anything on the bottom. That's it. That's the equilibrium expression. One more detail, you'll see these expressions are written with an SP, which stands for solubility product, because we're taking the product of these two ions to calculate solubility. So KSP value. I'm going to write this for the second one. The second one is pretty easy. It says KSP equals, okay, products on the top, and remember the reactants won't get included, so really just the products, which would be Ba2+ ion. No need to write an exponent here because the coefficient's a 1. SO42-, the other ion, again raised to the 1 power, so we write it just like that. One more example. When writing the third example, you will write KSP equals. You will take the products, which is Pb2+ and PO4 3-, and you will raise those each to the appropriate power. The PO4 3- gets squared, while the Pb2+ gets cubed in this equilibrium expression. These are two really important steps when you're calculating the solubility of different substances. It's the first step to finding solubility. Hope you can practice and get good at writing equilibrium equations and equilibrium expressions.